Hello, my name is Manal Parekh. I am a geotechnical engineer at the Risk Management Center in Lakewood, Colorado. Today I'm going to talk to you a little bit about internal erosion and specifically how it relates to the site characterization that we're learning about this week. Just a heads up, this is an overview of internal erosion. There is a more detailed training offered through the RMC that covers the fundamentals of the mechanics of internal erosion. So keep your eye out for that if you're interested in learning a little bit more. Here on the cover slide, you see a photo of what internal erosion manifests as in some cases, where you see particles exiting from an embankment and a little bit of a slump that occurs because of that. So we're going to talk a little bit more about these kinds of processes. Today we'll talk about what internal erosion is, how we categorize it by mechanism, and the locations where various mechanisms of internal erosion can occur. We'll touch on how we break down the internal erosion process from within the risk assessment framework, considering which mechanisms are feasible for site conditions. Throughout all this, we'll be discussing how site characterization is the basis for determining whether internal erosion poses a risk at a site. And hopefully I don't have to say internal erosion 1 million more times because it's quite tongue-tying for me. But we'll see. Let's start by defining internal erosion. It's the process by which soil particles that exist within an embankment or its foundation are removed from the soil structure under the forces of seepage or leakage. So soil particles must be able to be transported and must have a place for them to go in order for internal erosion to occur. We no longer use the terminology seepage and piping. It's a fairly general term. You're going to learn in this presentation some more specific terminology that better describes the mechanisms for various ways that particles can be transported and exit. So seepage and piping, a little bit dated. People will know what you're talking about, but we're going to try to be more specific, especially since we're thinking about site characterization and how the site characteristics can impact whether internal erosion will occur. Seepage and leakage are the primary driving forces behind internal erosion. So what's the difference? Well, seepage is flow of water, in our case, through a porous medium. Not necessarily a bad thing. All of our dams seep, but seepage isn't necessarily going to lead to any kind of a failure mode. That's one reason why seepage and piping terminology is not preferred, because it sort of has an implication that the two things always go together. Leakage, slightly different. It's concentrated flow through some path of least resistance, whether that's a crack in the soil, or a fracture joint, or a void in rock. Weepage, maybe that's what you do when someone uses the term seepage and piping, and that makes you feel like you're not so sure what they're talking about because you've taken this course and you'll know how seepage and leakage relate to internal erosion. So let's start by watching this animation prepared by ASCSO that shows the internal erosion failure mode occurring. So all dams and levees have some seepage as the water impounded behind them seeks paths of least resistance through the embankment or the foundation. So seepage needs to be controlled in order to prevent erosion of the embankment or its foundation, or to prevent damage. So internal erosion may be occurring if seepage rate is increasing and if particles are migrating through the structure. So internal erosion occurs when soil particles from within the embankment find a way to exit. What you're seeing here is piping, where there's a preferential path within a dam. We'll get a little more specific in this presentation and call that backward erosion piping. But if internal erosion is not detected, or if intervention is unsuccessful, this can happen. The crest will eventually collapse when the erosion path gets large enough and result in overtopping. So that was illustrated in the cover slide of this presentation. Mark Foster and colleagues at Australia's University of New South Wales have examined the statistics of large embankment dams constructed between the years 1800 and 1986. About 50% of all dam incidents are related to internal erosion, which can occur during first filling, at normal loading, as a result of degradation over time, or can be triggered by a sustained low water or record high loading event. To be clear, that's not to say that 50% of all dams have experienced internal erosion, but instead, of dams that have recorded incidents, 47%, or about 50% of those incidents, have been attributed to internal erosion. Internal erosion can occur as embankment materials erode into the foundation, through the foundation, or through the embankment itself, and that includes along conduits or structural penetrations. Evaluating internal erosion failure modes is very difficult because there's not one standards-based approach that allows us to simply model the physics of the internal erosion initiation, continuation, how it progresses, or ultimately leads to failure. So Terzaghi is correct here. We need to apply multiple tools, be them models, empirical data, and judgment to evaluate the potential for this process to occur. A risk-informed framework provides us with a great way to characterize the potential for the internal erosion process. It applies available standards-based tools and allows us to break down the process so that we can make judgments on the likelihood for each step to occur. Those judgments are based on the characteristics of the site that we learned through site characterization. This slide shows some of the various engineering evaluations, analysis, and processes that we use to evaluate the potential for internal erosion. However, there's no solution for these types of failures that can give us a factor of safety. Standards-based approaches provide us with the tools and information that we use, but we still are relying on judgment to assess if this is an actionable problem or if we consider the internal erosion for a particular site acceptable. Risk assessment is a way to work through the internal erosion failure modes for dams and levees. It allows us to specifically discuss, define, and describe the conditions, physics, and observations that contribute to failure or that restrict failure from occurring. How do we consider whether an embankment is a candidate for internal erosion to occur? This Venn diagram helps illustrate that the embankment is vulnerable to internal erosion when material properties, stress conditions within the embankment, and the hydraulic loading allow for particle detachment and movement. Initiation depends on some unfavorable coincidence of these three components, as illustrated in the diagram. So what are we looking for when we're trying to characterize a site, when we're thinking about whether internal erosion could occur at the site? So let's think about structural geology first. Look for fractures, jointing, bedding planes, faults, and characterize how far apart they are, how they're oriented, what the aperture is, and how continuous they are, so we can think about whether seepage can move through a feature and how much seepage and how much particle movement there might be allowed through that geologic feature. Large-scale geologic structures could influence the location and the frequency of these fractures, joints, and bedding planes, and also could influence what the groundwater conditions are, whether there are pressurized water conditions. Also think about the orientation of the dam relative to these larger geologic structures and whether that orientation is makes the structure more vulnerable to internal erosion or not. In our site characterization, we're also looking for geologic settings that might influence seepage and leakage, alluvial environments that might deposit point bars or sinuous soil, as well as places where fine soils may be deposited adjacent or over to sands and gravels. We're looking for jointed rock, areas of stress relief, or dipping sedimentary rock, specifically striking upstream to downstream or cross valley, striking at askew to the dam axis. Also look for geology that might be conducive to cracking, soft soils, wind-blown soils, expansive soils. Look for weathering effects, as well as cracking and earth fissures. Because internal erosion is a problem for dam and levee safety, terminology has developed over the years, with many different terms being used in the literature and by various federal agencies. This figure illustrates current terminology to describe the initiating mechanisms behind internal erosion. These terminologies can be observed in various case histories. The term process describes more phases of internal erosion than just the initiation. We'll get into that a little bit later in this presentation. The general mechanisms to consider for initiation are concentrated leak erosion, or CLE, backward erosion piping, or BEP, internal instability, also called suffusion or suffosion, soil contact erosion, or SCE, and internal migration, or stoping. Both CLE and SCE are considered forms of scour. ICOLD's Bulletin 164 on internal erosion presents CLE, BEP, internal instability, and SCE, but internal migration is terminology that's been added by the federal agencies. ICOLD Bulletin 164 describes stoping as global backward erosion and considers this a subset of BEP. The Corps of Engineers added soil in front of ICOLD's term contact erosion to come up with SCE in order to emphasize that this process occurs at the fine to coarse soil contact and not the soil to rock contact. The hydraulic gradient influences the likelihood of initiation and in some cases progression for each of these 5 internal erosion processes. For CLE, hydraulic gradient is used to estimate the shear stress for initiation. For BEP, it includes the vertical exit gradient for initiation and the horizontal gradient for progression. For suffusion, it includes the exit gradient for initiation. For SCE, the hydraulic gradient is used to estimate the Darcy velocity for initiation. And finally, for internal migration, a vertical down gradient is required. Concentrated leak erosion, also referred to as scour or tractive force erosion, abbreviated as CLE, as I said previously, refers to the internal erosion process that involves leakage flow through an opening in a soil or rock mass. Openings can be cracks, gaps, or other in the embankment or open defects in a soil or rock mass in the foundation. This process is distinguished by the other forms of internal erosion by the soil particles eroding from the sides of the opening, so along a crack, if you can visualize that. Leakage flow through the crack applies shear stresses or tractive forces on the walls of the crack, and this can lead to particle detachment from the walls of the crack. Case studies of Abiquiu and Worcester dams on Thursday will be presented, and on Friday, the case study of Keystone Dam address this particular mechanism for internal. So when characterizing a site, what are we looking for in order to identify the potential for CLE? Well, look for conditions that may be conducive to cracking, conditions that may result in differential embankment settlement, or look for actual cracks in the embankment or cracks in the foundation or foundation formations. A wide range of conditions that can create cracks or other defects where concentrated leaks can develop exist in dam and levee environments. I'm providing this list as a reference as things to look for when characterizing a site, either in the field or in design or construction records. So you're looking for things that can cause cracks, whether cracks are observed or defects are observed in the rock, or other differential thicknesses or differential settlement, desiccation, things like that. Here we see an illustration that shows some construction details to look for when characterizing the site. A little bit less about the site conditions, but more about understanding how the constructed features might provide paths for internal erosion around conduits or in poorly compacted zones. So understanding material types and construction practices that might lead to the potential for internal erosion. Soil contact erosion is also a form of scour, involving the selective erosion of finer particles from the area of contact with a coarser layer. Flow through the coarser layer runs parallel to that contact and can move particles into the coarser material's pore spaces. SCE occurs if the flow in a coarse layer is parallel to the interface between the coarse and the fine layer. Contact erosion or scour has been used in literature to describe erosion of core material at the core to foundation contact due to seepage flow within a continuous pathway in a rock foundation, such as an open joint. But this is really a form of concentrated leak erosion as we consider the types of internal erosion now. Corps of Engineers added soil in front of ICOLD's term contact erosion to emphasize that the way we think about this process is that it's occurring at the fine to coarse soil contact, not a soil to rock contact. So this is generally considered a contributing process, which means it can lead to the formation of a roof or a pipe for concentrated leak erosion. It's a little bit nuanced. So when characterizing a site to determine whether soil contact erosion could occur, we need to think about the materials that are at the site, how they're in contact with each other, what the material gradations are, and if that contact is continuous and what the orientation of that contact is, whether it's parallel to flow or not. Backward erosion piping, or BEP, initiates when soil particles detach and migrate under flow to a free, unfiltered exit. This process gradually works its way toward the upstream or flood side of the embankment or its foundation until a continuous opening, or what we call a pipe, is formed. Backward erosion piping is probably restricted to non-plastic soils or soils with limited plasticity. It mainly occurs in fine to medium sand with a coefficient of uniformity less than about 3 or 4, and that's based on experience and laboratory testing that has occurred in both the US and in Europe. BEP can initiate and progress at gradients likely to occur within an embankment or its foundation. Later this week, we'll hear a case history of Wapapello Dam as an illustration of BEP in the real world. This graphic shows the BEP process. First, we have flow in a sandy material below a more cohesive clay layer, shown at point 1. At a thin area in the cohesive roof-holding material, point 2, the flow exits without a filtered exit, forms a sand voil where the low cohesive sand exits under a zero effective stress condition. The detail A shows some of the small-scale processes occurring within the pipe or the opening, formed as flow at point 3 transports sand material at point 4 from under the clay. The clay holds a roof. The flow within the pipe has characteristics as shown in point 5, with friction at the edges of the pipe and possible turbulence within the flow path. Localized gradients may or may not be high enough to move particles to the exit point, as demonstrated at points 4 and 6. So what do we look for when characterizing a site in order to think about whether BEP can occur? Well, for BEP to occur, there must be a flow path or a source of water, an unprotected exit or unfiltered exit where the material can escape, and erodible material within the flow path that can be carried to that exit point. The material being piped, or the material directly above it, must be able to form a roof and support that pipe to keep that opening open. So look for these things when you're characterizing the site. Think about what are the material types that are in contact with each other. Is there an unfiltered exit somewhere? It could be quite far away. So you need to think about those things when you're looking at a site. And also think about, is there anything in the flow regime that could serve as a flow limiter or could serve to plug up or choke off the flow? So BEP can initiate at a point of heave where the condition in the soil results in an effective stress of 0 at the vertical seepage exit point. So in this top figure, you can see the heave point on the downstream end of an embankment, and on the bottom image you can see the heave point at the downstream end of a concrete structure. Few things to think about when trying to identify whether BEP could occur as a result of heave. Generally, heave is limited to cohesionless soils, might be indicated in areas that have experienced quick conditions or where there's been a volume increase in the soil mass. BEP can also initiate at a point of blowout. Blowout is sometimes also referred to as uplift or heave. It's a bit of a nuanced terminology, but generally uplift or heave of the underlying cohesionless material occurs simultaneously or immediately after blowout. Blowout being the rupture of a confining layer due to seepage pressures underneath that exceed the overburden pressure of the confining layer. So they burst through, the seepage bursts through this confining layer. It's generally limited to cohesive soils where there's a cohesive blanket with a pervious layer underneath. It can also occur when there are defects in the confining layer, such as cracking from desiccation or thin areas or penetrations like telephone poles or fence posts or that kind of thing. Internal erosion can also occur as a result of internal migration, which we also call gross enlargement or stoping. Internal migration is the vertical, progressive collapse and downward particle migration that occurs primarily due to gravity. This process can also be aggravated by seepage or precipitation, and usually manifests in a sinkhole that makes its way to the surface or an over-steepened slope if the process is occurring on the downstream or the upstream side. For this process, there's really no need for a cohesive soil to form a roof for the opening or the pipe. This is how internal migration differs from backward erosion and piping. Reclamation uses the term internal migration, which they formerly called progressive erosion. Again, don't get too caught up in the terminology, think more about the processes and what we're looking for in the field when characterizing a site that might support these processes in resulting in failure. But ICOLD, just another comment on terminology, ICOLD uses the term global backward erosion for this stoping type of process. Global backward erosion occurs when the soil surrounding incipient backward erosion pipes cannot support a roof and collapse. This mode may also occur in dikes or small dams constructed only of silty, sand, and gravel. If there's a potential for particles to be removed from the downstream slope by gravity, under the seepage gradient at a seepage exit where the phreatic surface emerges on the downstream face or toe. The failure mode in that case may look like sloughing or raveling of the downstream slope rather than formation of an opening through the embankment or a big sinkhole. So what do we look for when characterizing a site to determine whether internal migration, gross enlargement, stoping may happen? So we're looking for open voids, erosive soil particles, so we need to understand the material types. We need to think about, as there's a vertical progression under gravity, whether that materials above will be able to fall in to the void, and whether there's any seepage or precipitation possible that could aggravate the situation. So remember, internal migration occurs when soil particles drop into an open defect and then are carried away by seepage to some other exit point. If the voids are extensive in coarse soils or bedrock, that open exit might not be needed, but the exit, I'm putting that in air quotes, could be sufficient storage space for eroded fine particles to migrate into those cavities. So in that case, soil particles migrate downward primarily due to gravity, perhaps under seepage or precipitation forces as well. The process is repeated progressively, causing the void to enlarge and migrate vertically upward to result in a sinkhole. So the figure on the right kind of shows the stoping process and eventual sinkhole development into karstic limestone. So karst, obviously open void, but think creatively about whether other types of voids might exist in fractured rock or even in just very coarse material that has large pore spaces. Internal erosion can also occur when finer grain materials are removed through a coarser grain matrix. So that can be sands or silts moving through pore spaces in gravel, cobbles, or boulders. So the two terms that we use for this failure mode, the internal instability failure mode, are suffusion and suffosion. Suffusion is when the fines move through the coarser grained material, but the coarser grained materials have some point-to-point contact. So there's typically minimal volume change. In the case of suffosion, the difference here is the larger particles are not in point-to-point contact. The fines are mixed in. So when those fines are removed, we may see a volume change. This failure mode is less likely to occur in dams. When we're characterizing a site and trying to think about whether the materials may be susceptible to internal instability, we think about what the materials are. We typically need gap-graded materials in the embankment or the foundation to exist. So the most common geologic deposits for this type of material are glacial and alluvial fans that result in class-supported material, finer materials infilling the internal spaces. Also look for a loose framework of granular materials and think about the flow regime when determining whether the finer materials can move through the coarser materials. Suffusion is generally a contributing mechanism for other internal erosion processes. Remember, suffusion is the selective transport of fine particles from within a matrix of coarse particles, and then when those fine particles are removed from the coarse matrix, they leave behind the coarse skeleton. The effective stresses in this case are not loading the fine particles, so there's little to no loss of matrix integrity or change in volume. So whether that flow is downward or whether that flow is upward, the coarser materials are bearing the effective stresses. Localized increase in permeability may occur, but the movement of those free fines is independent of the stress condition. Suffosion is also a contributing mechanism to other internal erosion processes generally. Suffosion is the mass erosion of an internally unstable soil that results in a reduction of total volume and a potential collapse of a soil matrix because the fines are bearing stresses. And so when they're removed, the coarser particles reconfigure to bear that stress. The movement of these structural fines is therefore stress dependent, can be considered a form or contributor of backward erosion, but it's less likely to occur under the stress conditions and gradients in embankment dams or foundations. This graphic illustrates possible locations for internal erosion pathways. Example pathway 1 shows backward erosion piping in the foundation or at the contact between the core and the foundation. Pathway 2 shows a location where erosion of embankment material may occur into the foundation, so core eroding into the foundation. Location 3 shows erosion of core material through the downstream embankment shell. Location 4 shows potential concentrated leak erosion along a structure, whether that structure be spillway or outlet works. And then locations 5 show concentrated leak erosion pathways through cracks within the abutment. And those cracks may occur due to steep abutments and stress conditions associated with those, differential sediment, desiccation, earthquake cracks, or flaws in construction. So thinking about those locations of where internal erosion pathways could exist helps us think about the design process, the construction process, whether there are design flaws, construction flaws, material types that are incompatible and in contact with each other, whether there are geologic anomalies that concentrate seepage, or reasons why cracks might form. So that's what we're looking for when we're characterizing a site. Generally, internal erosion associated with through penetrating structures is essentially a subset of internal erosion through the embankment, and it's often seen as concentrated leak erosion. Another location where internal erosion can occur is into tow drains or stilling basin under drains. This generic sequence of events helps us break down the internal erosion failure mode in order to identify where site characterization can help out. So the sequence of internal erosion generally consists of 4 phases: initiation, where the erosion starts based on geometric conditions and hydraulic conditions, continuation, progression, and then ultimately failure and breach. So where site characterization fits in, we're going to talk a little bit in the following slides about that, but generally it fits in identifying whether the conditions exist for initiation, continuation, and progression. So for analyzing engineering risks, we typically use event trees as a common approach for dam and levee safety risk assessments. An event tree shown here is a graphical representation of the sequence of events that lead to a set of outcomes. So the outcome is generally breach. So event trees like this are used to obtain quantitative estimates of the probability of dam or levee failure and the associated consequences. The sequence of events from the previous slide are translated into this generic event tree shown with the 4 general phases: initiation, continuation, progression, and breach or failure. The events may be further decomposed into other necessary events in order to fully evaluate the failure mode. So we'll talk a little bit about how site characterization fits into these phases. You may have noticed on the previous slide that we can decompose initiation into 2 nodes on the event tree. The first node considering scenarios where the likelihood of a flaw is a primary factor in the event tree. That flaw can be a physical condition that allows seepage concentration or leakage through an embankment or its foundation. So that can be a crack, a void, the presence of erodible material, or a material incompatibility. So we focus our site characterization and investigations on understanding whether the likelihood of a flaw exists or what that likelihood might be. Then we consider as the second node hydraulic conditions that might initiate internal erosion at that flaw. Bear in mind that if you count an unfiltered exit as the flaw, for example, for a backward erosion failure mode, be cautious not to double count the lack of filter elsewhere. So as a little bit of a spoiler, we'll talk about node 3 coming up soon, which is continuation, and that's generally where filters kick in to halt the failure. So just be cautious that you're not double counting. How does an open flaw get created to get internal erosion rolling? Well, cracking occurs in soils when the stresses in the soil exceed the minimum strength capacity of the soil. So this can happen through hydraulic fracture, which involves the formation and extension of an opening in a soil mass due to increasing water pressures. Recognize that these stresses are inevitable even in well-designed and constructed dams and are not necessarily caused by poor design or construction practice. Cross-valley differential settlement may lead to extension strain cracks in low-stress zones subject to hydraulic failure. So as a dam is constructed, partially saturated compacted soil in the embankment consolidates and settlement occurs. Where the valley side slopes are steep, as shown in this upper left figure, or there are steps in the profile, as shown in this lower left figure, differential settlements can occur, and these can lead to tensile or low stress zones where cracks may form and hydraulic fracture can occur. Here on the top right, we see an effective step caused by 2 different stages of embankment placement. So if the material properties of one stage vary from the material properties of another stage, that can cause differential settlement as well and cracking. And then here on the bottom right, we see a abrupt irregularity in rock foundation. So this is a smaller scale feature that maybe might occur somewhere like here or here, that results in arching across that abrupt change and an area of low stress that also may be susceptible to hydraulic fracture and cracking. So differences in the foundation compressibility can also lead to fracture. So same thing differential settlement. So imagine here in the foundation or here in the foundation, you have zones of variably compressive material. The foundation may settle differentially and also cause cracking. So similar to how these figures are shown, but the material differences are not so much in the embankment, but in the foundation. Cross-valley arching can occur in narrow and steep valleys. In conditions like this, vertical stresses are shed onto the sides of the valley, which can lead to hydraulic fracture within the embankment. And that's a vulnerability for internal erosion. If we have stress conditions conducive to a flaw, we next consider whether particle detachment can occur. For the various internal erosion mechanisms that we've talked about so far, CLE, BEP, suffusion, suffosion, SCE, and internal migration, we need the critical hydraulic load to provide sufficient energy, as well as the material to be susceptible to erosion, so have low erosion resistance, as well as the critical stress condition that results in the flaw. Those things need to occur coincidentally in order for internal erosion to initiate. So whether CLE will initiate depends on the location and the orientation of a crack within an embankment or its foundation, and the hydraulic forces through and along the walls of the crack. So we're looking at, are the imposed shear stresses greater than the critical shear stresses of the soil, and is the flow velocity enough to transport any detached particles through the crack? Whether BEP will initiate at a site depends on whether a continuous permeable layer exists from upstream to downstream, and whether the seepage exit gradient exceeds critical values, so whether there's sufficient gradient to move soil particles at the downstream end and progress that toward the upstream. So once internal erosion is initiated, it will continue unless the eroding forces are reduced or the passage of the eroded particles is impeded in some way. So erosion may be interrupted or arrested through filtering action in downstream materials in the embankment or foundation. So we ask, is the passage of the detached particles interrupted or stopped by filtering action? Or is the exit unfiltered or inadequately filtered? So is there a free or open space for the erosive material to just exit right out of without having to pass through any other zone? Be aware that many existing dams have filter or transition zones that are coarser than required by today's filter design criteria. So keep a lookout for that. For internal migration, the effective opening size of a defect, say in a conduit, in a pipe, or in a culvert, or in a soil or rock mass, may limit the continuation of internal erosion for that mechanism. So here we show some typical unfiltered exit locations in these graphics, but these don't represent an exhaustive collection of where unfiltered exits can occur. The figure at the upper left shows internal erosion through the foundation occurring into a foundation drainage blanket that doesn't necessarily meet filter criteria and exiting to a free face, or alternatively into a coarser layer that also does not meet filter criteria. The figure at the upper right shows internal erosion through a homogeneous embankment and exiting out of a free face. The bottom left is kind of a zoom in of the top left, showing internal erosion into open joints or defects in the foundation. And then finally, the bottom right shows internal erosion occurring into conduit, or also this could be through a wall or into rock, allowing soil particles to pass. So again, tying continuation and filter considerations back to site characterization, what do we need to be thinking about? So gradation and the ability to adequately retain particles is really the most important factor in continuation. But even if a filter or a downstream zone exists, there could be other factors that affect the likelihood of continuation. So consider cracking based on fines content, presence of plastic fines, cementation, potential for washout due to segregation or internal instability that results in a coarser filter gradation than was originally constructed? Is the filter width adequate? Is the durability of the material such that degradation due to weathering or breakdown of weaker particles could take place? Was overcompaction a part of the construction that might result in brittle zones? Could there be heave due to insufficient cover if the filter is the only material on the downstream embankment face? Is the filter sufficient permeability? Are downstream zones performing their required drainage functions? What is the continuity to an open face or an extensive void space in coarse soils or bedrock for eroded finer particles to travel to? Some of these things are affected during handling, placement, and compaction of the filter. So these are things we should be looking for when we're characterizing the site, again, both in the field or using documentation and research about what we know historically about a site. So again, we ask what the site characterization consideration should be during progression, which is the third phase when we look at the process of internal erosion. We're mostly thinking about the mechanical conditions that exist and the material properties. So we're thinking, is a crack sustainable or does it collapse or self-heal based on what materials are eroding? Is there an upstream zone that supplies particles or a downstream zone that traps the eroded particles? So is there some kind of filter action or clogging action that might go on? And then is there an upstream hydraulic cutoff that is a zone of finer grained granular material or a concrete face slab or a core wall or a cutoff wall that helps restrict the hydraulic conditions? Let's look at an event tree for BEP and think about how site characterization provides information along that tree. So I've pulled in some images here to kind of refresh our memory about the internal erosion BEP process. And I've circled in red along the tree where site characterization is a major player, where geologists and geotechnical engineers can help determine if the material properties and continuity contribute to the failure mode. So for example, if erosive materials are encountered in a single drill hole somewhere in the site characterization process, whether it's in historic data or whether it's in new explorations, does that mean that backward erosion piping will occur? We need to consider the realistic variability of the deposit. Does the erosive zone have some continuity? Does it go directly upstream to downstream, or does it exist along a more tortuous path because of its depositional environment? So is that path continuous? Also, do the material properties provide any kind of filter action, or is the exit unfiltered without any material filters? And then also further along in the progression node, does a cohesive layer exist that's continuous and consistent enough to hold a roof? So those three red circled areas are areas along the event tree when we're thinking about this from a risk framework where site characterization plays a key role in the assessment. Here we've done the same thing, providing the event tree for CLE internal erosion failure. Pulled in some images to refresh our memories about CLE and what causes cracks, and circled some areas along the event tree, both in the initiation phase, the continuation phase, and also in the progression phase, to think about where site characterization feeds in to determining whether cracking has been observed or may be likely based on site conditions. And again, whether material types provide for filtration, whether sidewalls are of the type that will maintain a crack, and whether there's any upstream zoning or any zoning at all that will limit flow or self-heal within the crack. So these circled red circles indicate places where we can provide information from a site characterization standpoint to feed into how we evaluate risk along the event tree. So in this presentation, we've done a bit of a deep dive into what internal erosion is, how we categorize it by mechanism, and the locations where internal erosion can occur. We considered how site characterization is the basis for determining whether internal erosion can occur at a site, And we also looked at how site characterization feeds into the risk assessment framework for internal erosion failure modes. And I think I successfully said internal erosion over 1 million times in this presentation. Luckily, I had the benefit of being able to go back and re-record slides, or you would have heard me mispronounce it a lot. This is a list of some of the references in this presentation. If you saw a citation or an image that you wanted more information about and it's not shown on this list, just let us know and we'll provide that to you. So thanks for your attention in thinking about internal erosion, and site characterization. Feel free to address me or any of our other instructors with questions, comments, or discussion within the chat, or if we have time, we can talk openly right now. Thank you.